Hello everyone. Well, if you're working on R, this week we're going to finish up our look at time series analysis by looking at a couple of different models. And you've gone through the chapters, you've gone through the data camp module that I posted for you last week. But what we'll do is we'll take a look at some, 3 examples, and you get a chance to see kind of how you can assess the quality of models that you're creating to actually do your predictions. So the first thing we'll do is we'll load up the data sets, and then we'll look at what's in our data sets. We'll make a couple modifications to our data set so we can get a better picture of what the data set looks like once it has been made to be stationary by creating a differenced data set. Those are 2 words that you probably have seen in the book or in the data camp. Once we decide we've got a data set that is set up, then we'll go ahead and run 3 models on it. We'll run a model that will set up a baseline, and that will run a couple of models to see if we can improve on that baseline. And by improving on that baseline, what we're trying to do is really account for the variability and come up with something that is a better fit to the actual data, so that when we project into the future, we will have the most intelligent and the most finely tuned model to make those projections. Okay. So I've created the script, and the script has a lot of documentation in it, and hopefully that documentation will be helpful. But what I'm going to do is walk real quickly through the script and just tell you what it does. The first thing, and I'm going to talk about everything that's not documentation. The first thing we're doing here is a new command, and it's a new command that I'm going to give you that's going to be helpful to you, potentially. And it's when you've loaded a bunch of script and you've loaded a bunch of files and you've got variables that you use, and sometimes you might be using variable names that are similar between one script and another, and you're not sure what's populated and what's not. And if you get something that's populated and you don't repopulate it, that can really mess you up. So this rm command actually lets you remove, and the parameters that you're feeding it is list equals ls kind of everything. So what this is basically doing is going through your current workspace and taking all variables that have been populated and depopulating them, or clearing them out. It's like starting off from a clean slate. So that's what that command is doing. We have 3 libraries that we're going to use: library FPP2, and library Forecast, and library ggplot2. You're already familiar with Forecast and ggplot2. You probably already have those on your machine, so running a library command on those will load those, and that'll be fine. You may have to go get FPP2. FPP2, in a lot of ways, is a concatenation of both the Forecast and the ggplot2 libraries with some enhancements and improvements. And so some of the functions that we will use in this script are actually located in FPP2. If you don't have it, go write your install packages to go get it and get it loaded into your space so that we can actually run with this. Next thing we're going to do is we're going to load the data set. So this is very simple. We created a variable called data. Kind of an unfortunate named variable, but it works for us in case we want to use the script with multiple data files. We can read in whatever we want to read in using read CSV, and then the file choose allows us to go out and use the Windows tools to be able to get whatever file we want. Once we've done that, we can set up our first time series analysis. We chose the variable y. Variable y is really kind of, it's a common nomenclature for predicted. And what we're doing here is eventually we're going to be predicting the next 2 years worth of information about this particular data set. So we're going to use that variable. And that variable is going to be populated with the results of a time series where we've used the data file that we just loaded in. We're going to use the second column, so we're going to focus in on the second column. We haven't really used this syntax yet. And the first column is just going to kind of come along for the ride. And then we're going to start with the set up the matrix of 1992-1. That's the very first year in the file. The file contains 27 years of information on retail sales around the country, broken down by day of month. And then we're going to go ahead and look at the frequency. The frequency is 12. So each set of data is, of course, 12 entries. Let's go ahead and run the script up until then. Data file is loaded in. It's called, and I put it into documents actually, retail sales. And once we have that data file in as data, we can set up our first time series analysis, and that's now done. Once we have the time series analysis done, we can then take a look at the file. What's actually in our file? What does our file look like? Now, remember, I said this is retail sales by day of the month. So it's average retail sales per day of the month for the last for every month for the last 27 years. So I've got a couple of things that we can do here. I'm going to take a look at the retail sales and see what we've got. See if our plot looks like it's trended. See if our plot looks like it has seasonality, because when we want to do our projections, we want to make sure that we account for both trending and seasonality in our projections. So we have this function called Autoplot. And Autoplot, it comes along with the libraries that we've loaded up here. And Autoplot will allow us to sort of plot out our time series analysis, and we can give it some GG title. We can give it the Y labels. We can give it X labels if we wanted, whatever. But this is pretty simple and straightforward. We've just given it a title. We've just given it a vertical axis. And when we hit Autoplot, that's what we get. Okay, Autoplot shows us from the 1st of January of 1992 all the way up to the last of May of 2019. And it's showing us the average retail sales in millions of dollars per day. So in January of 1992, which is this very first data point here, we had over 4,000 millions, or $4 billion worth of retail sales each day in January. And that's what it's accounting for here. And because it's a line chart, there's a lot of line that doesn't really matter. It's going to be the points that we have here. And so when it goes up, we see that it increases. We'll get to a peak or a valley, or a peak or a valley. But the one thing that we really notice first off is that we have a trend. Now, these are not corrected dollars, so that's a little bit biased in the sense that the data here in 2019, it's going to be higher partly because we're buying more, and partly because things cost more, because we're measuring dollars. So this line might not be as trended, but I'll give you a little tip. The little tip is that when I did see this data that was corrected for the consumer price index changes, it really didn't look much different. So we are just generally buying more stuff in 2019. You'll notice here in 2008 what happened when the economy crashed. Retail sales went way down, and it took a while for them to rebound. And once they did rebound, they went way up. So that's what we have. We can see already that we have trends, and we can see already that we have looks like seasonality because we have fairly even spikes. Okay, let's go ahead and close that out. Let's take a look at a way that we can eliminate the trends. Now, there's a function in R called diff, and we're looking at it right here. And what we're going to do is we're going to take our data set, and we are going to feed it into, and the data set is actually now time series analysis. We're going to feed that into this diff function. And what this diff function does is it removes the trend. And it removes the trend by comparing like the month of January of 1992 to the month of January 1993 to the month of January 1994, and so on and so on and so on. And we get to a point where we're comparing month over month across the years, and that allows us to account for the fact that year over year there are some differences, and this diff function removes those differences. It doesn't remove the variability, but it removes the differences that are afforded to the years, that are caused by the years. So we'll go ahead and run that. And when we do that, we want to do the next autoplot. The autoplot's the same as we did before, but instead we're using dy instead of y. The dy, the d of the dy stands for differenced with a d. And what that means is it means that we've basically removed the trending. We'll go ahead and plot that, and you see now we have a data set that is called stationary. It's stationary in the sense that the trend has been removed. So we can look across this, and we'll still see the seasonality, we'll still see the variability, but because we did the diff function, we've removed that kind of vertical line that was the trend. And so that makes it easier for us then, without the trend in place, to then use this data set or this time series to make projections. One thing we still have though, we still have the seasonality. And because we have the seasonality, we want to take a look at that. And the first thing we're going to do is we're going to run a plot that allows us to look at it year over year or year by year. And the second thing we're going to do is we're going to group it instead of by year, we're going to group it by month. So by grouping it by year, let's see what we can learn about seasonality of this data set. And we can see different colors for different years. And there's your legend over there. But they all seem to follow the same pattern. And in the sense, the same pattern is that retail sales are pretty low in January. They seem to go up quite a bit in February and remain static, maybe dipping a little bit during the summer, and then they shoot up off the charts in December. December, of course, is because of Christmas time. So this plot seems to suggest that people kind of spend all their money at Christmas time and then don't spend any money in January. But that allows us to see that there is a trend. There is a seasonal trend that kind of follows year over year. Let's take a look at another plot. And that other plot is allowing us to see that same data, only this time we're going to see it by month. Okay, and these are all the Januaries, these are all the Februaries, these are all the Marches, Mays, or Aprils and Mays, etc. You see that this Decembers are kind of, when compared to the Januaries, they're just kind of opposite ends of the spectrum. So we are looking at quite a dip in January, and we're looking at quite a spike in December. Here's why this matters. When we look at it and we see the seasonality, the next thing we're going to do is we're going to consider the seasonality when we build what's called a baseline or a benchmark. And what that is all about is that let's take a crack at this. Let's take a crack at actually looking at this particular method, whatever method we choose, and we'll go ahead and use that method to project all of the existing months. And then we'll check to see how much we are off, right? We'll look at the residuals. If we have a model that actually is able to predict the months that we have, and it's able to do it very accurately, then we'll have very small residuals. And when we calculate a couple of metrics, we'll be able to see that those residuals are small. Then we might want to look at a couple of different methods. And if we look at a couple of different methods, we're hoping to find a method that where the residuals are the measures of residuals are smaller. And ultimately, we'll get to a place where we've got a couple of them. ETS and ARIMA actually search through multiple combinations, and they look through multiple potential models, and will find us the best possible model. So those are very convenient. But what we're interested in doing here is we're just going to create a benchmark. And to decide what method to use to create the benchmark, we might want to look at our plots. And one of the easiest ways to be able to sort of project future months is to take the mean of all past months. Well, we could look at this data set and think that that's probably not a great idea because we have such outliers. The outliers being the months of January and the months of December. And it's not just one. It's, 27 years times 12, 390 some odd of outliers. That's going to really pull our average off. And so averaging them across all 390 some odd entries is not going to be an accurate way to do this. So we're going to throw that out as even a consideration for what we would use for benchmarking. What we might use instead is a naive method that accounts for seasonality. So the naive method is really, it's not terribly complex. It will look at it'll look at the entire data set, but it will try to correct for seasonality. And so it will come up with a potential projection. Let's go ahead and run that. We'll actually run that and drop that into a variable called fit so that we can go back and print fit and check the residuals on fit. So we'll start that by running it. That's done. Let's move this out of the way now. We don't need this any longer. And we're going to print. And then we're going to do checksum. I'll do checksum in a minute. What I want to do is I want to go back up to the top. And there's one metric I want to draw your attention to. And that metric I want to draw your attention to is going to be residual standard deviation. Okay? There's going to be a residual mean, and then there's going to be a residual standard deviation. If the mean is small, the standard deviation will be small. If the means the residuals are large, and the mean will be large, the standard deviation will be large. So we want this to be as small as possible because we want the model to be as close as we could possibly get when we're actually making our projections. So we're going to go ahead and say this is our projection. This is our benchmark or our baseline. It's 240.74, the standard deviation. And again, it is a measure of how different our model is from actuals, and it is a good metric to use. Okay, so I've even popped this into the script. The standard deviation is 240.74. Now, the other thing we're going to do is we're going to check residuals fit. Check residuals is a function, and we're going to do it on fit because that's what we created when we ran the naive method. Okay, create 3 plots. Okay, it gives us a little bit of an idea of how far our residuals are from our actuals. Okay, and it also gives us information about autocorrelation and how the residuals are distributed, if they're distributed evenly or if there are spikes in the residuals. Okay. Now, when we do time series analysis, what we're really trying to do is we're really trying to come up with a method that uses all of the information and pulls all the information into our model. Okay. Thus, if it does a good job of pulling the information into our model, we should have very small residuals, but the residuals also should be very different. So you should be able to see patterns in the residuals because there shouldn't be patterns in the residuals because they should be very small. In this particular case, we're not doing so well because we have these lags, and a lag is basically it's each shift. If you take your 370 or 390 whatever different entries and you make a copy of it, and you take that copy and you shift it down one, and then you run the correlation, that's what's called an autocorrelation. And each time you shift it down one, that's called a lag. So we do it up to 36 times. So we can check the autocorrelation 36 times, and these are of the residuals, not the original values. What we're seeing here, though, is that there's a lot of autocorrelation because these correlations are getting up into the 0.4 area, 0.3 area, and that's too high. And what that tells us is it tells us that the model that we created didn't take into account enough of the information about the data. It wasn't a good model because now we still have autocorrelation. And remember, the residuals should be small and they should be entirely random. If we're seeing patterns in the residuals, it means that the model isn't as good of a fit as we would like. The other thing we're seeing is that we're not really evenly distributed when it comes to the residuals. So that means that there's spikes and there's some skew in the residuals. So things, again, residuals should be entirely random. They should be entirely no pattern to them at all. We're seeing patterns here because we're seeing autocorrelation and we're seeing some skew. All right, so this one, while it does give us 270.4 for the standard deviation, let's see if we can do better. Okay, so we're going to move on and we're going to use a function called, or a method called ETS. And ETS is for exponential smoothing model, or ETM, I should say. ETS, I guess. And we'll go ahead and run that on the data set. We'll hit fit ETS is going to be the variable that we use. And we just run the function ETS, and that's part of the libraries that we've loaded in. That's done. We can go ahead and print those, and then we can go ahead and check residuals. I'll do that in a second. Again, one of the things I want to draw your attention to is sigma. Sigma is 246.6073, so I put that in there. That's actually worse than what we had up here. So it's not a better model. We have higher means on the higher mean probably on the residuals, and the standard deviation is higher, so there's more variability. And then if we go ahead and run the check residuals, we're seeing things, it doesn't look any better. And in fact, it looks probably worse. So we've got a lot more autocorrelation, and we've got a lot less, even the prior distribution chart showed us, or histogram showed us, better distributions than this. So we'll go ahead and throw this one away and say this one's not any better. So let's go down to the next one, and the next one is going to be an autoregressive integrated moving average. So a little bit about this. You probably already know this from your reading or from the data camp, but moving average is where you select some number of prior months. It can be 6 months, it can be 12 months, it can be 18 months, and you calculate the mean. When you calculate the mean, you take that mean, and that becomes the next month forecast. Okay. Then what you do is you include that new month, and you go back your 6, 12, or your 18 months, whatever you're using, and you calculate a new mean. And that becomes the second new month that you forecast. And now you calculate the third one by including the two new ones that you've created, and you go back to 6, 12, or 18 months, and so on and so on and so on. That's why it's called the moving average, because it is a moving average. It literally is a moving average, and it's starting to integrate the means of what you've created. This is an autoregressive integrated moving average, and I'm not going to go into the detail about what the autoregressive piece means, but it is basically going back. And it's similar to linear regression, but it's basically going back and using prior months instead of calculating sort of a slope and an intercept, just using prior months, which is what I just explained moving average does. And this is the ARIMA, the ARIMA model. And we're going to try that next. And so we're going to create a variable called fit ARIMA, into which we're going to auto-populate or populate something called auto-ARIMA. Auto-ARIMA is a nice little function in the sense that, remember, this is moving averages. So it's going to go in, and we'll specify that we're going to use the Y time series. We're not going to use the difference time series because ARIMA will take care of that for us. It'll take care of trending for us. It'll take care of seasonality for us. And we specify a couple of variables. We say that the stepwise is equal to false, the approximation is equal to false, trace is equal to true. These are all things that we can get away with, and I'm just going to give you kind of a skirt over on the details of this. We're going to get away with this because we're looking at such a simple file. So it's not going to go through and do all this exhaustive sort of work for us. It's just going to skip most of this stuff. But we specified that we're in fact using the original file, and it's going to run through a whole bunch of different ARIMA models until it finds the one that it thinks works the best. So we'll go ahead and run that. And this takes a while to run, so you'll see that your machine will grind away for a while until it actually gets through all the possible models. And it will give you a result that basically says, this is what I think is the best model. Then what we can do is we can print the information that comes out of this summary, and we can go ahead and look at the residuals and see how our model looks. Okay, So it gives us the best model. 3.1.0, 0.1.2, these are not points, they're commas, and 12. I'm not going to go into the details of what that means. What I'm going to go into, though, instead is what is my measure of quality of this model? And we're looking for R squared. That's the last one. Oh, I got to print. Let me print first. There we go. All right. Then we're looking for R squared. Sigma squared. Okay, sigma squared estimate is 35,366. Well, sigma squared is basically the standard deviation squared. So we have to take the square root of 35,366 to get to our measure of what the comparable value would be to the standard deviations from the first two models. And I already calculated it for you, and it is 188.0585. Okay, that is the square root of that value, and so that is our standard deviation. So this turns out to be our best model. It's our best fit. So let's actually prove that and take a look at the check residuals. Well, now we're doing better, okay? Because if you notice, the scale on the side has changed to 0.1 and negative 0.1, and only a couple of them are tripping up past 0.1 or past 0.01, or negative 1, no, negative 0.1, whereas before we were all the way up to 0.4. So that's better. And this looks like a much more even distribution of our data sets, or of our residuals. So these both seem to indicate that we are better. We're not perfect yet. We still have some autocorrelation built into this, which means that there's not as much randomness in the residuals as we would like to see. And this is indicated here as well, but it is vastly improved. Okay, so now we've made a decision. We had the baseline, which was basically the S naive, and then we had the ETS, which didn't look much better. In fact, looked a little worse than the S naive. And then we ran the ARIMA model, the ARIMA Auto, which actually went through and found us a really good model to use, found us the best one we could use. So now the last thing to do is, okay, now that we've built the model, let's use the model. Okay, so we're going to forecast with the ARIMA model. That was the best one. So we'll use a variable called forecast, FCST, and we're going to set that equal to the results of forecast. Our data is our fit ARIMA, that is the model that we created, and H equals 24 is the number of periods that we want to forecast for. So we'll go out 2 years, and we'll say, let's see if we can figure out what retail sales are going to be in 2 years. Let's go ahead and run that. That's done. Then we're going to autoplot. We're going to autoplot whatever we just dropped into FCast, and we're going to include 60. What does include 60 mean? If I do nothing, and I say nothing on that include, then it will cram all 390 or 300, however many months we have, into the data set. And what we're actually predicting doesn't look very good. So we're going to go ahead and shave that off. And we can see, just include the last 60. I don't really want to see everything, all 390. I just want to see the last 60. So that's going to actually make our our plot a little more useful. This legend equals true turns out doesn't really do anything, so I'll leave it in there, but it's not really giving me a legend, so I need to go ahead and fix that command. So we'll go ahead and autoplot that. And there it is. And it looks pretty good. Now, if we want to print the summary information for FCast, we can do that as well. And that gives me this information, and it shows me what my projections are. Okay. And these are my projections. So for January, remember, the data set I have stopped at May of 2019. So my projection for June is here all the way through to the May of 2021, which is 2 years out. And it's given me kind of, you know, a little bit of other information, but really at this point, the thing I care about most are these values. So I can look at it visually, and it shows me with a confidence interval of 80% and a confidence interval of 90%, that's the two different shades of blue, it's showing me what my projection is going to be starting in June of 2019 all the way up to 2021, May of 2021. It respects my trending, it respects my seasonality. You can see that the seasonality is built in. You can zoom in on this if you need to. If I need the actual amounts, those are included here. These are the forecasts. And those are what I could actually put into a report or something like that if I needed to do that. Okay, that is the file that I've given you, or the file that I built this with. What I'm going to do now is I'm going to give you a different file. And I'm going to give you, instead of it broken out by month, I'm going to give you a file, or broken out by day, I'm sorry. I'm going to give you a file that shows the retail sales for the entire month. Okay, so the file looks very, very similar. But you'll get a different plot. You'll get different plot points and those kinds of things. So I will post the script. I will post the original data file that we used in the script in this video, and then I'll post the one that I want you to use when you go through and run the script. Okay? Let me know if you have any questions.